right, so we're going to finish up section 4.2, which is on rational functions and their graphs. Okay, I'm just going to write down a description of what we already did and what we're going to do. And you don't have to copy it down. I just want you to know where we're going. So yesterday, all the functions that we graphed, the degree of the numerator was less than or equal to the degree of the denominator. That's the type we did yesterday. Okay, today, we're going to graph rational functions again, but this time the degree of the numerator is going to be greater than or equal to the degree of the denominator. So the degree of the top is going to be bigger than the bottom. That's the only difference. Okay, it does change how we do a few things, so I'll show you what you need to look for when this happens, when the degree in the top is larger. Okay, when the degree in the top is larger, we get this new thing called an end behavior asymptote. So suppose we had a function f of x. That's our rational function. The top would be a polynomial, which I called h of x, and the bottom would be a polynomial I'm calling g of x. Okay, in a real example, those will all be numbers and something we can actually work with. If we do out the long division, we're going to get a quotient, and we're going to get a remainder. And I just want you to remember kind of how that works. Okay, so if you take 3, divide it into 16, 3 goes into 16 5 times, and you can write remainder 1, right? Or, if you want to write out the answer like this, it's the same as 5 plus your remainder over 3, over your denominator. So 3 divided into 16 is 5 1/3. Quotient plus remainder over your denominator. Right? We're going to do the same thing with a polynomial. So you'd have a quotient, you'd have a remainder over your original denominator, g of x. The only difference is q of x, r of x, and g of x might not just be numbers, they're algebraic, they're expressions. Okay? They're polynomials. And the only thing that's really important here is q of x, the quotient. Q of x is what we call the end behavior asymptote. Okay, so to find an end behavior asymptote, you just do out long division and look at the quotient. So what's nice is you're not doing anything new. You've done long division before. You found quotients, you found remainders. We're just calling the quotient a new name now. We're calling it end behavior asymptote. Okay? But it's going to be all the same steps you already know for long division. Synthetic division won't work here, especially when the denominator is more complicated. Right, so synthetic division would work for this one, but let's use long division because we can't always do synthetic. Okay, so let's find the quotient, the remainder, and the end behavior asymptote. Well, once we have the quotient is the end behavior asymptote. They're the same thing. Okay. So let's do out the long division and see what we got. So we have x minus 2. Divided into 2x cubed minus 4x squared. Before I put the plus 3, what do I want to be careful about? Something's missing here I need to put in. Yeah?
X.
Yeah, what should I put in for the x term?
0.
Yep. If I don't do that, things aren't going to line up in nice columns. Okay, let's divide it out. Okay, this part is what we did a couple weeks ago, so this is old news stuff. So 2x cubed minus 4x squared. Subtract. 2x cubed minus 2x cubed is gone. Negative 4x squared minus negative 4x squared. That's gone. It's negative 4x squared plus 4x squared. So now I bring down, I have 0x plus 3. That's the only thing that's left. But we're basically done because x, you don't even need this term, it's 0. X doesn't divide into 3. Okay. So my quotient is the 2x squared. And then my remainder, that's the 3 part. So let's just write down quotient, which I'll just put in parentheses. That is the end behavior asymptote. That they're the same thing. 2x squared. And the remainder part is 3 over my original denominator, x minus 2. Okay, now I want to look, what happens to the remainder part when x starts to get really big? What number does this fraction approach as x starts to get real big? There? 0. Pretend x was 1,000,000. 1,000,000 minus 2, still a huge number. 3 divided by a huge number, very small. So the point here is the remainder part, as x gets bigger and bigger, the remainder part gets smaller and smaller. So that's why we don't even need it. And the end behavior asymptote is just the quotient. The remainder doesn't even make a difference. When x gets huge, infinity. Okay. So any questions on how we found the quotient, which is the end behavior asymptote, or the remainder part? Okay. So there's 3 kind of important points here to understand. There's a difference between the end behavior model, which is what we did yesterday, and the end behavior asymptote. Okay, the difference is, to get the end behavior model, take the leading term in the top and you divide by the leading term in the bottom. End behavior model is easy. It's very fast. End behavior asymptote, that's when you use long division. Also, end behavior asymptote is only something that we're doing when the degree in the top is larger than the degree in the bottom. We didn't do this yesterday because we didn't have any problems like I just explained. Sometimes the end behavior model and end behavior asymptote are the same. Sometimes they're different. It depends on the problem. In general, in this section, we're going to focus on end behavior asymptotes. End behavior model is something we usually do when the degree of the numerator is less than or equal to the denominator. And we touched on this idea yesterday about when you get certain kinds of asymptotes. So number 3 summarizes the types of problems we had yesterday. If the degree of the numerator is less than or equal to the degree of the denominator, that's when your asymptotes are straight lines. Horizontal lines, vertical lines, even lines on a diagonal. We'll see one like that today. Okay, but this is really just summarizing the types we did yesterday. We didn't see a diagonal line yesterday, diagonal asymptote, because that falls under the type when the degree of the numerator is bigger than the denominator. So we'll look at one of those or two today. If your asymptotes are not linear, okay, if they're not lines, they actually can be curved. Okay, you can have asymptotes that are curves. So it's a curve that your graph gets closer and closer to, instead of like a horizontal or vertical line. Those are a little tricky to draw. We're going to try drawing one with curved asymptotes, and it's going to be the only one we do. And I'm going to try to keep the curve relatively simple, meaning I'm not going to give you like a cubic polynomial for an asymptote. We'll maybe do like a quadratic. So it's like a parabola shape. It's a little easier. Okay, does everyone have those three points? Right, so graphically, before we try to even sketch the example we just did, right, I want to verify that the end behavior asymptote we found actually works for example 5. Okay, so what we're looking for here is when we graph this end behavior asymptote and we graph the original problem, as x starts to get huge, g of x should basically look exactly like f of x. I'm not saying they're going to look the same near the origin. This is end behavior as x is towards infinity and negative infinity. Okay, so let's type in f of x. Okay, so we've got 2x cubed minus 4x squared plus 3. And we're going to divide by x minus 2. Okay, now we found our end behavior asymptote was 2x squared. Let's start off with a standard window. So what's in red is the end behavior asymptote. What's in blue is our actual function. Okay, let me just double check I typed everything in. Yeah, thank you. I forgot the division. Okay, let's see. Yeah, that's more what it's supposed to look like. So you can kind of see a parabola shape to it on the left, not near the origin. Okay, end behavior is not for predicting near origin, it's predicting far out. But we're not seeing the right-hand side of the parabola anywhere. It just looks like it drops down forever. It's probably because it's up off the screen. Okay, set the y-max a little higher. And then maybe we can start to see what was hidden before. Okay, so the basic shape of this graph is a parabola. Okay, on the left side, in fact, the red line is almost directly on top of the blue line. On this side, you can see the blue line and the red line kind of getting closer and closer together until they're almost on top of each other. It's just that there's some weird behavior right near our vertical asymptote. Okay, because we have a vertical asymptote at 2. So we'll just have to investigate 2.01, 1.99, and see what happens. Okay, so we've done example 6. Okay, we've confirmed that 2x squared predicts the behavior of this function as x starts to get farther away from the origin. And in fact, if you do like zoom 3 and zoom out, they're going to look more and more identical. Now the red line is almost completely on top of it. Okay, except there's something weird happening around the vertical asymptote. All right, so let's go through how you would sketch that. Okay, first thing you want to do if you're going to sketch something like this is find your end behavior asymptote. We've already done it, and let's sketch it. Okay, make sure you notice my y-axis goes by 2's, the x-axis goes by 1's. To graph y equals 2x squared, I would just plot some points. Okay, when x is 0, y is 0. When x is 1, 1 squared is 1 times 2 is 2. And keep in mind that this is symmetrical. When x is 2, we get 2 squared is 4 times 2 is 8. 2, 8, and negative 2, 8. Now let's do one more, 3. 3 squared is 9 times 2 is 18. So remember, this is my asymptote. This isn't my graph. It's what my graph is going to look like as x gets big. So I'm going to try to draw this in with a dotted line. Okay, best I can. I also have a vertical asymptote when x equals 2, because if you plug 2 in, that would make the denominator 0. Okay, so let's put that line in. Let's kind of investigate what's happening on each side of that asymptote. We don't need y2 anymore, we just need y1.
What did you plug in to get the shape of the graph?
The shape, I plugged in 0, 1, 2, and 3 for x.
The value?
Yep, the EBA, the end behavior asymptote. So I wanted to sketch my end behavior asymptote and my vertical asymptote. Right, now let's pick some values. Let's try a value just before 2. Let's try 1.99. Okay, we're at negative infinity. Let's try a value just after 2. Positive infinity. And keep in mind, our graph is going to be pinned in between these asymptotes. So if I sketch this up further, the top portion of this graph is going to be pinned in between the green line and the red line. So there's going to be some very sharp curve in there. Exactly where? Well, maybe we want to try a couple more points. All right, let's try when x is 2.5. Okay, let's see where we're at. We're at, what's that say, 18.5. So at 2.5, we're at 18.5. Okay, and you could keep trying, but it's going to start to go up very quickly. So even if you tried like when x is 4, I can't graph that, it's way off. So it's going up very sharply there. Okay, so let's try to connect what's happening in that section. Okay, it's going up forever there. It's coming up forever there. But it has to go through this point down here. Okay, so it's going to come down. It's going to curve pretty sharply. And it's going to go back up. This right-hand side of what I just drew, that's the edge of my end behavior asymptote. It's getting closer and closer to it. All right, now let's try to figure out what's happening on the other side. So we have this point. I feel like I need some more points. I'm not really sure. Let's try when x is 1. Y is negative 1. So when x is 1, y is negative 1. Remember, my y-axis goes by 2's. Still not too sure. Let's try when x is 0. Y is negative 1.5. So negative, let's see, that'd be negative 1. Almost down at negative 2. Okay. Let's try negative 1. See where we are there. Okay, now we're up at positive 1. So I'm starting to see kind of like there's going to be a curve. Let's try one more. Let's do negative 2. We're up at 7.25. Somewhere around there. So our curve is going to stay very close to that red line. It's going to come down. It's going to kind of curve. Something on that idea. Okay, let's look at the graph and see how we did. That's pretty much what we have. Okay, this section in the upper right, okay, that's that section, and then the curve comes down, kind of curves and goes down. I'm not going to be overly picky about the curve, just have the general idea. Right, so that's a tricky one to sketch. Okay, that's the only curved asymptote we're going to do. Any questions on that? So same idea as what we did before, but you might need more points. And I mean, I did. I needed like 7 or 8 points to try to get an idea of the sketch. All right. Let's try this one. I want to kind of compare this to the last one. If you look at the last problem, Kelsey, what was the degree of the numerator in the last problem? 3? And how about the denominator? 1. What's the difference between 3 and 1? 2. And notice our asymptote was a degree 2. It was a parabola. Okay, let's look at this one. Okay, Alex, what's the degree of the numerator here?
2x.
The degree, so just a single number. So the degree is the term that has the highest exponent. Highest exponent. That's the degree.
2.
Highest exponent in the numerator is a 3. So it's a degree 3 polynomial. Okay, the bottom is a degree 2. Right. Cody, what's the difference between 3 and 2?
The 2 is going to be a parabola. The 3 is going to be, I don't know what you're saying, 1.
Yeah, the difference here is only one number. Okay, since the difference is only a 1, the asymptote that we get here isn't going to be curved. Okay, it's going to be a degree 1. Okay, degree 1, those are equations like y equals mx plus b. Those are straight lines. They might be on a diagonal, but they're still straight lines. All right, so let's make a little space here. Okay, let's do out the long division. So we got x squared plus 2x minus 3 divided into 2x cubed plus 7x squared minus 4. Now, all I'm really interested in here is the quotient. I don't need the remainder. I'm trying to find the end behavior asymptote. Okay, that's what I want to find. So that's just the quotient. Right, so x squared goes into 2x cubed. You get 2x. Multiply it back out. And you know what I should do? Don't forget a 0 for the linear term. Doesn't affect anything yet, but it will eventually. Okay, so 2x times x squared is 2x cubed. 2x times 2x is 4x squared. 2x times negative 3 is negative 6x. Subtract. Those are gone. 7x squared, take away 4x squared, is 3x squared. 0 minus 6. Minus a minus becomes a plus 6x. And then bring down your next term, but you're not going to need it because I'm not interested in the remainder. Yeah?
I don't know, positive 7x squared and positive 4x squared.
We subtracted. 7 take away 4.
Uh,
Yep, so you're always subtracting. Okay, double check, make sure I didn't make a mistake, but I think it's okay. Now divide x squared into 3x squared. You get a 3. There's your end behavior asymptote, 2x plus 3. There's no reason to keep going unless you want the remainder. Okay? And if you wanted to keep going, now you'd multiply the 3 out, and then plus 6x, and then minus 9. I'm going to stop though. Okay, then you'd subtract. Okay, but I don't need the remainder. That's what I was looking for. Yeah.
So how do you know when you're looking for the end behavior asymptote
You're look,
the model.
end behavior asymptote only applies when the degree of the numerator is greater than the degree of the denominator.
So if it's greater on the top, then you have to do the whole division. But
Yeah.
if the bottom has the higher one.
Yeah, if it's equal or the bottom has the higher one, like we did yesterday, that's usually when we look for an end behavior model. Yep. Okay, so there's my end behavior asymptote. Let's draw in the line 2x plus 3. Okay, y-intercept at 3, slope is 2. Up 2 over 1. So let's see, maybe about like that. Oops. Close enough. Okay, now we need to find if there's any vertical asymptotes. Okay, to find the vertical asymptotes, I'll factor the denominator. And if it doesn't factor, I'm going to have to use the quadratic formula, but I tried to pick one that would work out nicely. We're going to need a plus minus. And you're going to want to do a 3 and a 1, and put the 3 with the positive. So it's x squared, take away x plus 3 is a plus 2. So Casey, what are my vertical asymptotes here? 1 and negative 3. Okay, let's draw those in. We got one at 1, negative 3. Right, you know what I'll do? Let me move the move this down a little bit. So we really have 6 sections here. Okay, on the left, we have this big section in the top and at the bottom. In the middle, we have one at the top and bottom, and on the right, in the top and the bottom. Our graph is going to be trapped inside those sections. And usually, we only use 3 of the sections to draw the graph. Okay, let's start on the left-hand side. Okay, what would be a good value to check that's just to the left of negative 3? Oh, Cole? What would be a good value to check that's to the left of negative 3? Yeah, let's type that. Do I have my function typed in? No. So it's 2x cubed plus 7x squared. Plus x squared minus 4. Divided by x squared plus 2x minus 3. Okay, so I'm going to try what Cole said, negative 3.001. And we're at negative 990. Okay, so we're way down. Yeah, just make sure. I'm going to put the numerator in parentheses, just in case. And let me double check. 2x cubed, 7x squared minus 4. Okay. So negative 3. Yeah, did that just change? Yeah, it said negative 990, and I didn't think that was right. So apparently, order of operations, if you don't have the numerator and denominator in parentheses, you get it wrong. So that's actually a good thing to learn right now. All right, so we're at way up. We're actually at positive infinity, which is what I was thinking. All right, let's try another value. Let's try negative 1, 2, 3. Let's try negative 4. Give us a little bit better idea. Okay, at negative 4, we're at negative 4. It's right about there. Yeah. Okay, and the idea is it has to stay trapped between those two asymptotes, and it's just going to keep getting closer and closer to them. So in this section, it's basically going to look like that. All right, let's look at the middle section. Okay, to do that one, I'm going to try some points on each side of the asymptotes and probably a couple other points to help me out. Let's try negative 2.99. That's fine. Okay, the point, it's going way down. Okay, let's try 0.99. Going way down again. Okay, so somehow it's going to be getting closer and closer to that, closer and closer to that, but I don't know what's happening up towards the origin. So let's try negative 1 and 0. Okay, at negative 1, we're at negative 1/4. And at 0, we're at 1.3. Okay, I think I have enough points I can kind of see what's happening. So it's staying very close to that line. It's coming up, staying very close to that other line, going through those points, curving, and coming back down. Okay, and the last part. Let's try just a value a little bit bigger than 1. Okay, try like 1.01. Positive infinity. Okay, and if we try a couple other points, you're just going to see you're going to end up trapped in that top portion, right, like this. All those pieces, they keep going. Let's look at our sketch, see how we did. All right, so we're zoomed so far out in the middle, the calculator is not sure what to do. Try your standard window, see if that looks a little better. Yeah. So here's the left part that's curving down, kind of the part in the middle that has that sharp turn, and then just seeing the very tip of the top portion. Yeah, but that's kind of the process of how you go through it. Just have to plot some points, and I would use the calculator as much as you can to help you. Okay, so that asymptote, because it was on it was a diagonal, we call it a slant asymptote. Okay, on the test, this is probably the kind of asymptote that I'm going to lean towards doing. It's a little easier to draw than a quadratic one because it's quadratic curves. But it's a little harder than a horizontal because it's on a diagonal, it's not horizontal. Okay, any questions on example 7? Yeah? Why is it in only those sections? It just has to, I mean, we found that just by plotting points. I would just say plot points. Yeah. Now, if you reflected everything, then you could start to get some different pictures here. Okay, but just plot points and use that to figure out what sections it's in. And use the asymptotes to kind of guide you, keeping the graph trapped between those lines. Okay, this one we're going to skip over for now. Maybe we'll come back to it. But I just want you to try to tell me what the asymptote is going to be, the end behavior asymptote. Is it going to be a parabola? Is it going to be a slant asymptote? Okay, just by looking at it. Go ahead, James.
Slant,
Yep, you're right. How do you know?
because x squared minus x is just 1 exponent, so.
Yeah, if you subtract their exponents, it's only a difference of 1. If there's a difference of 1, you got a slant asymptote. If you have a difference of 2, like if you had an x to the 10th in the top and an x to the 8th in the bottom, that's going to be a quadratic asymptote. Right? So you'd have a slant asymptote. You'd have a vertical asymptote at negative 2. I know that x plus 2 is not a factor of that numerator. I can tell just by looking at it. So you get your vertical line. You're going to have that. This time, though, I think you're only going to have one vertical. One vertical, one slant. So it's going to simplify your picture a little bit. There's only going to be 2 portions to this graph instead of 3. Let's look at this one. This one is way too complicated to try to do by hand. So I just want to graph it and show you something you need to be careful of if I give you that on the test tomorrow. Let's type it in, see what we get. So 2x to the 4th. And remember what we learned last time, keep both numerator and denominator in parentheses. Okay, plus 7x cubed, 7x squared plus 2x, divided by x cubed minus x plus 50. Now I would expect there to be some kind of slant asymptote here. And there will be. Let's just start with a standard window. And if you set your Ymax higher, you do see that this line actually starts to curve out, and you get a slant asymptote, kind of right in there. Does anything here look like we would need to investigate it a little bit more? There's something here I don't like in that window. I'm looking at it and it looks a little suspicious to me. Yeah?
Shouldn't it have like another, shouldn't you make your window bigger so you can see more?
Okay, you can set your Ymax bigger. There's nothing really more that we're going to gain and see here. It's going to kind of just keep doing that thing on the top part. Kind of curves back a little bit. But you're getting a horizontal slant asymptote. But there's something in this window that it just looks a little funny to me. Something that I think I need to take a closer look at to see if it really looks the way the calculator is showing it. Yeah?
That it's getting very close to the x-axis.
Yeah, something in here really close to the x-axis. That looks way too flat to me. Okay, it looks perfectly flat. But let me zoom in a little bit and see what's really happening. So I might ask you, how many times does this graph cross the x-axis? I have no idea from that picture. Okay, let's set our y min and max. Let's zoom way in. Negative 0.5 to 0.5. So now the whole screen is going to be just one unit from top to bottom. Okay, starting to see something, okay, in that space. Let's try even 0.1, negative 0.1 to 0.1. Now I'm really starting to see something. So my point here was, if you see something that looks really flat for a long time, it probably isn't. So in this case, if I asked you how many times it crosses the x-axis, I think it's 1, 2, 3, 4. But I'd have to zoom in even a little bit more to probably confirm that. But it looks pretty close to 4 times to me. So make sure you be careful of I call that like hidden behavior. Can't really see it in a standard window. Okay? And that's it. That's all I wanted to show you for that problem. Okay, and this one, which will probably be our last one. Okay, I want to take a look at all the rectangles that have an area of 200 square feet. Okay, let x be the width. What I want to do is find an algebraic representation and a complete graph of P of x, where P of x is going to represent the perimeter of this rectangle as a function of x. After we do that, we'll use the graphing calculator to find the dimensions of the rectangle that would have the smallest perimeter. So you could think of this problem if you were building a fence, and you wanted to fence in an area that was 200 square feet, and you wanted to use the least amount of fence possible to do it. That's basically what we're doing in this problem. Let's start with our rectangle. They tell us the width is x. What would the length have to be? If the area is 200 and the width is x, think about length times width has to equal 200. So what would you have to put in for the length? So when you multiply it by x, you get 200. James?
Would be 200 divided by x.
It'd be 200 divided by x. Yes. Because now if you did length times width, you'd get 200. Good. Now I want a formula for the perimeter. Well, now that we know the length and the width of our rectangle, the perimeter should be easy to find. As long as you know the relationship between the sides of a rectangle. Anyone think they could give me a formula for the perimeter of that rectangle? Oh, Augustine? How about just start and tell me what's the formula for the perimeter of a rectangle in general?
Length times width.
That's area.
Oh, wait, no. Per 2 length plus 2.
Okay. 2 length plus 2 width. Do we have a length in this problem? Yeah? Do we have a width?
Yeah.
Mm-hmm. So we just have to fill in our particular length and our particular width. So let's start with what you said, 2 times the length. What would double my length be here?
400 over x.
Yep. Plus double my width?
2x.
2x. There we go. That's what we're graphing. Now earlier we found a common denominator and we put all this together. You could do that if you wanted. It's not necessary. Common denominator would be x. And you'd have to multiply top and bottom by x. The only reason I might do that is now I can see I should be getting a slant asymptote. The degree in the top is 1 bigger than the degree in the bottom. Okay? But again, that part, it's not necessary. Let's just graph the original. 400 over x plus 2x. Okay? Just keep it simple. Yeah.
Why'd you put the 2x over 1?
Well, I was saying earlier if we wanted to find a common denominator and put it all together, then we'd have to, like if I wanted an end behavior asymptote here, you can't have 2 separate fractions. It's got to be all together. But in this case, we're just going to graph it anyway. Right? So don't worry about the common denominator. All right, so we had 400 over x. And I probably should put that in parentheses. Plus 2x. Right, let's try to use a little bit of common sense. We're not going to have negative widths, so don't let that be negative. X max, well, that could really go as high as you want. You could have a really, really long and skinny rectangle. Yeah?
So how do you find the end behavior model?
End behavior model is usually something we do for the types of problems we had yesterday. That's when the degree of the bottom is larger than or equal to the top. In this case, the degree in the top is larger. So we wouldn't be finding an end behavior model, we would look for an end behavior asymptote. All right, let's look at some y values. Okay, like when x is, well, we couldn't have 0 width. That wouldn't make sense. When x is 1, y is up at 400. So a standard window is not going to work very well. Let's set our y max up to maybe 500. So that curve represents all the different perimeters. So now you could tell me a value. If x is 5, your perimeter is 90. If x is 6, your perimeter is 78. I'm looking at, is there a minimum? Okay, and there should be. Okay, this should start to curve back up. Let's set the x max bigger. Okay. Now I think we can see clearly that there is a minimum somewhere in here. Okay. I want to calculate that minimum, and that'll give me the smallest perimeter. So let's do second calc minimum. Okay, I'm watching y, I'm at 65, 56, I think I saw 57 in there. 56. Okay, somewhere there's a minimum y value. And it says that the minimum perimeter you could have would be 56.6, and that's when the width is 14.14. So x, which is the width, is 14.14. But I still need my length. How can I get the length once I know the width? James?
Plug it into 200 over x.
Plug it into 200 over x. So 200 divided by 14.14. 14.14. So what does that mean? It's a square. We've done this before. I've told you that if you want to have a shape where you need the minimum amount of perimeter, but you want to enclose the maximum amount of area, the shape is always a square.
What was
Right.
the perimeter problem?
What was the perimeter column?
No, what did we get for perimeter?
Oh, what would the perimeter be? The minimum perimeter, I think, was, well, it'd be that number times 4. Roughly, it was about 56. I think it was 56.6. Did they ask for the minimum perimeter? Find the dimensions. So in this case, you actually didn't need to find the perimeter that was the minimum, just the dimensions of the rectangle. All right, so the homework will be on page 235. Okay, it's 38 to 43, 45 to 47, and then 51, 52, 55, 62, and 63.